All right, hello. I am making this video so that you can have a little bit of a review before your quiz, which is going to be during discussion next week. So you have the weekend to kind of look over this material, and it's all based on what I had gone over in lecture on Wednesday yesterday. So group activities 9A and 9B, I'm picking the questions here that I want you to be looking at for the quiz. So group activity 9B is the first one. And the first question has to do with the Rydberg equation. And it says a line in the Lyman series. So that's a band in the spectrum of hydrogen, and it's also given that it's ultraviolet, and you're also given that it's a transition from an upper level to n equals 1. So they have they're saying the same thing 3 times. The Lyman series involves ultraviolet light, and then they're also saying n equals 1. So any ultraviolet transition will always be a transition from some upper level down to n equals 1. So you got 3 ways to know that this is ultraviolet, and final here is going to be equal to 1. All right, so you're given the Rydberg constant, which is 1.097 times 10 to the 7 meters to the minus 1. And you're given that the wavelength is 9.50 times 10 to the minus 8 meters. So this would be 95 nanometers. Sometimes you're given the wavelength in nanometers. You want to convert to meters because the meters here, for example, have to be consistent with the meters of the Rydberg constant. So you always want to go to meters. Students tend to mess up the whole thing just because they're not clear on that point. Get rid of that. Okay. All right. So then you're going to use the Rydberg equation. This is not given. 1 divided by lambda is equal to r times 1 over n final squared minus 1 over n initial squared. So you want to put in everything you have here. 1 divided by lambda, the wavelength, which you want to have in meters, 9.50 times 10 to the minus 8 meters. Okay. And that'll be equal to 1.097 times 10 to the 7 meters to the minus 1. That's r. 1 over n final. This is n final right here. So 1 squared, okay, and then minus 1 over n initial squared. The question is, what is n initial? What is the level that the transition starts at or goes from to get down to the ground state of n equals 1? All right, so then 2 ways to do this problem. One is to factor the Rydberg constant into the terms in parentheses. So you'd multiply the first one times it and then the second one. I don't recommend that. Instead, take this number and divide this side of the equation by it, and then divide this side of the equation by it as well. So you'll see how much easier it is to do the second method. Okay, so 1 divided by 9.5 times 10 to the minus 8 meters and 1.097 10 to the 7 meters to the minus 1 is equal to, some people like to write this out, 1.097 10 to the 7 meters to the minus 1 divided by 1.097 10 to the 7 meters to the minus 1. Some people like to do it that way. Some people just do it in their heads. But I'm giving it to you this way. All right, so then this part cancels, right? And then you're going to combine the two terms on the left. So this will be 1 over 1.042. Now notice what you got here. You got -8 and +7. So if you just add those two together, it's -1, right? So 10 to the -1. So you expect it to be, you know, a small number, not huge and not tiny. All right, so then this will be equal to 1 over 1 squared, which is 1 minus 1 over n initial squared. Okay. All right, so then on the left-hand side, 1 over 1.042 is going to be 0.9596. And this is 1 minus 1 over n initial squared. Oh, I don't need that anymore. Okay. All right, now we want to subtract 1 from each side. So subtract 1, and you're going to have, let's see, 0.9596 minus 1 will be equal to 1 over negative n initial squared. And the left-hand side, this is 0.40, and that is negative. And then you have negative 1 over n initial squared. So the little math trick here is that you can flip both sides. Oh, and also the negative signs cancel. You can flip them. All right, if you flip one, you can flip the other. There's other ways to do this, but that's kind of fun. So 1 divided by 0.040 would be equal to ni squared over 1, right? So then 1 divided by 0.04 is 25, is equal to n initial squared. Then you take the square root of 25, square root of ni squared, and then I'm going to put them on the other side. N initial is going to be equal to 5. So this means that the transition in the ultraviolet region of the spectrum, 1, 2, 3, 4, 5, right? This is the transition right here that results in light that has 95 nanometers. Okay, so that's the first one. I want you to be able to do that. In class, it was a different one that we did. In class, we were given both the initial and final, and we had to calculate the wavelengths. So you should be able to do it both ways. All right, then the second problem here is on the quantum numbers. And it says, give an example of an orbital represented by. So give an example of an orbital represented by n equals 3, L is equal to 2, M subscript L is equal to 2, and M subscript S is equal to 1/2. So these are the 4 quantum numbers. N is the principal quantum number, L is the azimuthal quantum number, M subscript L is the magnetic quantum number, and M subscript S is the spin quantum number. So you need 4 to completely describe an electron occupying an orbital. And the information here tells you what the orbital is that's being occupied. So we have n can go, starts at 1. It can be 1, 2, 3, 4, and so on. In this particular case, it's 3. We have the rule for L. So n starts at 1, 2, 3, 4, and so on, all the way to infinity. L starts at 0, 1, 2, and goes up to the value of n minus 1. All right, and then M sub L, well, we'll get to that. So we have this right here, 3. We have this right here. And so L represents the subshells that are called S, P, D, and F. And so S corresponds to the L value of 0, P corresponds to 1, D corresponds to 2, and F corresponds to 3. The L values, all right? The L value says something about the shape and the type of orbital. Okay, so you can have a P subshell. You got 3 P orbitals within a P subshell, for example. All right, and then, so this is saying so far that we have a 3D, right, orbital, 3D, or 3D subshell. Now we want to specify which orbital it is. So we're going to take the value for M sub L, take the value of 2 here, and you go 2, negative 2, and then all integer values in between. So 2, 1, 0, negative 1, and negative 2 would be the 5 orbitals. So this is for the orbitals here. 5 orbitals, and they're the d orbitals. And then we have names for those as well. dxy, dxz, dyz, dx squared minus y squared, and dz squared. Okay, so there's no real correlation between the number and the name of the orbital, right? Name of the orbital's down here. So in other words, 2 here might correlate with dxy, or it could be dxz. It just has to correlate with one of these in the set of 5. Excuse me. So you just pick one. We'll just call it that one, okay? Could be any of the 5, and that'd be fine. So then the orbital represented by these 4 quantum numbers is going to be 3dxy. Now, the last quantum number indicates that there are 2 electrons that will fill into this 3dxy orbital, and one spins clockwise, the other one counterclockwise, and the number representing that is a half and negative a half. So you don't put it into the orbital designation, but you know that there are 2 electrons that can fill, a maximum of 2 electrons that can fill into that. All right, and then number 3, a little bit more on the quantum numbers. So here, what is wrong with the designation? That doesn't either. For an orbital, n equals 3, L equals 3, M subscript L, 2, they call it sub, M sub L, and M sub S would be a half. So what's wrong with it? What's wrong is this one, L, because L can only go up to n minus 1, right? So this particular example, L can only be 0, 1, or 2, but it can't be 3 because it has to be 3 minus 1 as the last one here. So that's what's wrong with that. N cannot be equal to L. All right, we'll skip the next one on the photoelectric effect. And then, hold on. We look at 9b, and you want to look at the first 2 examples in 9b. And the first one is give the electron configuration of phosphorus. All right, so you have to go to the periodic table for this, and you're going to realize that phosphorus, symbol is P, has 15 electrons. It's element 15, number, it's in position 15 because it has 15 protons, but in order for it to be neutral, it has to have 15 electrons as well. Okay, so it's got 15 electrons, and here you need to know you need to know the the electron configuration: 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and so on. In this case, you only get 15 electrons, so it's 2 plus 2 is 4, 6 is 10, 12 here, and then you're just going to have, instead of 6 here, it'll be 3. So for phosphorus, it'll be 1s2, 2s2, 2p6, 3p3. Okay? Nope, I forgot one. 3s2 and 3p3. Okay, so this was just an exercise here. You're supposed to have that memorized. Okay, so we can just erase that. Get it out of the way. Okay, so that was the question. That's the electron configuration, but let's go ahead and draw the orbital diagram for this one as well. So the orbital diagram is the one that has the energy levels. So you start with 1s, then 2s, 2p, 3s, 3p, 4s, 3d, and then there's 4p and so on. We don't need that many here. So we've got a total of 15 electrons. 1, 2. So if the first one fills spin up, the next one fills spin down, 2 maximum per orbital. 2, 4. Then when you have p, you have px, py, pz, and going across it's 1, 2, 3. And then you come back and fill the second electron into each one. 4, 5, 6. So that's 2, 4, 10, 12. And then you got 3 more, 1, 2, 3. So 3p3, which is what we have up here. Whoops, 3p3. And that's this part right here. Okay, so that's the orbital diagram. You have some information there, but also then you have the orbit diagram. And I just want you to differentiate between the two. Or 3 of them: electron configuration, orbital diagram, and orbit diagram. So the orbit diagram, 1, 2, 3. So this is like the classical picture here, where the electron just goes around in circles, right? And we know that that's not exactly the case, but sometimes that model is useful. So n equals 1, n equals 2, and n equals 3. All right, so then for n equals 1, you just have 2, right? Then for n equals 2, you have a total of 8. 1, 2, 3, 4, 5, 6, 7, 8. And then for n equals 3, you have a total of 5. 1, 2, 3, 4, 5. Just spread them out kind of evenly like that. All right, so nitrogen and phosphorus are in the same group. Phosphorus is right under nitrogen, and they both have that same property that when they form the ion, that they want to be the 3-. So you know about nitrogen 3-, right? Nitride. Phosphide is the same. Where does this come from? It's this business about the octet rule and how each one of these orbits wants to, or at least up to n equals 2, wants to be 8. N equals 3 can either be 8 or it can be 18, depending. So, but in this case, phosphorus wants 3 more. I'm going to put them in 1, 2, 3 in order to have 8 total, and n equals 3. And so that's why you're adding 3 negatives, and that's why you get the designation P3-. All right, so in blue is just P, right? Just phosphorus by itself. But if you add the 3 electrons, then that's for the notation for P3-. Okay, just a little bit more information there. And then the last one I want you to look at is I think it's copper. Wait a minute, let me look at it. Question. Okay, so this is number 2. And this says draw the orbital diagram for the valence shell of copper. Yeah, and also a point about the valence shell, without these 3, just the 5 here, these 5 electrons are the ones that are involved in chemical reactions. And then these 2 represent the core. So these n equals 1, n equals 2 electrons, they represent the core. And then without these red ones here, these 5 represent the valence electrons. Those are the ones that are involved in chemical reactions. Okay, so oftentimes we're just interested in what's going on with the valence shell, and that's what this is here. So copper turns out to be an exception. We'll go ahead and start with the electron configuration of copper, Cu. And if you look in the periodic table, copper has a total of, I believe it's 29, is that right? 29 electrons, yeah. And so we write it out, 1s2, whoops, 2s2, 2p6, 3s2, 3p6. So far we have 8 and 2 is 10, so we have 16. Then we have 4s2, that's going to make, missing one, hold on, 10, and 10 is 20. Okay, that's right. And then you would say 3d9. Okay, and so this then would be the valence shell electrons. Some people argue whether the 4s2 is part of that or not. Depends on things, whether they're involved in chemistry or not, but we'll stick with that for the moment. This would be the core, and these would be the valence shell electrons. Okay, so, but this is an exception. Copper and chromium are the 2 exceptions you need to know. What happens in copper is one of these electrons hops over here so that the 3D subshell is filled with 10 electrons. So this is not correct here. The true electron configuration, 1s2, 2s2, 2p6, 3s2, 3p6. And then it goes 4s1, 3d10. All right, so that is the correct notation for the electron configuration. And so it wanted the orbital diagram for it. So the orbital diagram is going to be 1s, 2s, 2p, 3s, 3p, 4s, 3d, 3d, and then it would be 4p on top of that, but we're not going to use that one. All right, so you got a total of 29. 2, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29. So this, let me erase the 4p here because that's in the way. And what happens here, of course, is that this one electron hops over here so that the top part, just this top part right here, would be 4s1, 3d10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, so this part would be wrong. All right, so that's the electron configuration. And if you want to look at the, that's the orbital diagram, sorry, orbital diagram. And if you want to look at the orbit diagram, you'll have here n equals 1, n equals 2, n equals 3, and n equals 4. So you're going to have 2 in the first one, n equals 1. There'll be 8 in the second one for n equals 2. 3, 4, 5, 6, 7, 8. N equals 2. N equals 3. You're going to have 3s, 3p, and 3d, right? So there's 18. Just remember I said it could be either 8 or 18 for n equals 3. So this is n equals 1, this is n equals 2, n equals 3. Can be either 8 or 18. It would be 18 maximum if it's a transition metal. All right, so then for n equals 3 is 18. 1, 2, 3, 4, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, where we want to put them, 18. All right, and then we got 1 and n equals 4. So this is n equals 4 out here. That's the only one for n equals 4. All right, now we'll look later on at the reverse process of removing an electron or more than one electron to form the ions. But I'll tell you now that the n equals 4 electron goes out first because it's further from the nucleus. So if you wanted to make copper plus 1, it's just the removal of this one right here. All right, we'll talk about that next week, I think. Okay, so let me think of what else I wanted to tell you about. Let's see, I think there was one more thing here. What was it? Well, also, chromium is the other exception. Cr is 24 electrons. 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, okay, 3d5. So in this case, you've got 4s, 3d. It starts out 1, 2, 3, 4, 5, 6, like that. And then this one hops over here so that the correct configuration for chromium, 4s, 3d, 1, 2, 3, 4, 5, 6, like that. This is the half-filled shell. This is half-filled. There's stability associated with half-filled shells. And in this case over here, there's stability associated with the filled shell. And, as compared to the non-filled shell where the electron's on the other side. And if it's more stable, then it'll just spontaneously be formed. It'll just naturally go over to that. So there's other examples of exceptions. These are the two that I want you to be able to reproduce on a test. And I think that's it. So this is going to be the material for quiz 3, which will be Monday afternoon. Monday at 11, I should say, and Wednesday at 11. All right, I'm going to make a video now, YouTube video.